So if we did things in an order, we could find our x-intercepts and y-intercepts first for curve sketching, then look if there's any asymptotes if needed. Then you could look at your first derivative and second derivative tests, find your maximums and your minimums and your inflection points. Find out where it's increasing and decreasing, where it's concave up and concave down, and then sketch our graph. So we did the first two already. And here is the third one, the rational graph. So I'll put up the graph here so we can see overall what it looks like, and you can check how you did. Got a couple of points on there and a couple of asymptotes. So starting off, if we were starting off looking at our x and y intercepts, our x-intercept, if we set it equal to 0, the only time a fraction is equal to 0 is if the numerator is equal to 0. So we look at that 3x plus 1. Is that ever equal to 0? Yes, at negative 1/3. So that's one point here we have on our graph, negative 1/3 comma 0. For our y-intercept, if we plug in 0 for x, we get 1/4. So we've already got 2 points on this section of the graph. For our asymptotes, to find our vertical asymptote, we're looking for a non-permissible value. You don't want to divide by 0, and when x is negative 2, then our denominator would equal 0. For our horizontal asymptote, we're looking at what happens when x gets really, really big. The idea of a limit. And the idea of a limit, as x gets really, really big, and we just sort of put infinity in here to represent that. If you had 2 times infinity and you added 1, that adding 1 wouldn't really make much of a difference. Same thing on the bottom, that adding 4 wouldn't make much of a difference. So as this gets bigger and bigger and bigger, this basically becomes 3x over 2x. And so our horizontal asymptote is at 3/2. So as a starting point, we've got 2 points. We've got both of our asymptotes. And now we can look at our calculus to see whether we have maximums and minimums, what happens when it's increasing and decreasing. So if we find our derivative and our second derivative, and we simplify those expressions, our first derivative is 10 over 2x plus 4 squared. Our second derivative becomes negative 40 over 2x plus 4 cubed. Both of those, if you set them equal to 0, again, a fraction's only equal to 0 if the numerator is equal to 0, and 10 and minus 40 are both never equal to 0. So this graph is going to have no stationary points and no inflection points. But we can still check for concavity and still check when things are increasing and decreasing, because we would put our critical point, our non-permissible value, in there. So when we're making our number line, we're putting not only where it's equal to 0, we're also putting non-permissible values in there. So when we put in negative 2, and then we check before negative 2, and we plug it into the derivative, it's positive. And after negative 2, it's still positive. So this function is always increasing. Okay. And same thing with our second derivative. We can check before and after negative 2 to find out where things are concave up and where things are concave down. So now taking this information back to our graph, at this point, we would have had both of those asymptotes, and these 2 points would have been our only 2 points. So at this point, as far as graphing this nicely, I have 2 points in this section to the right of this asymptote. I have no points to the left of that asymptote. So it's not a bad idea just to plug in a value of x. Since our asymptote's at negative 2, a reasonable value would be at negative 3. Plugging in negative 3 into the original function gives us positive 4. So we have another point that our graph goes through. Now, in order for our graph to go through this point, negative 3, 4, to show the asymptotic behavior of approaching the asymptotes, and we know it has to be concave up and increasing, the only possibility is the graph that you see here. So it has to go through that point, it has to be increasing, and it's naturally going to be concave up as a result. And since we had these 2 points to the right of that vertical asymptote, we would know, since it has to be increasing and it has to be concave down, that that's the shape that it would have to be. So the rational graphs are a little bit different with calculus because all the special things that we learn about calculus, maximums and minimums and inflection points, and none of them happen, it's kind of a little bit disappointing, but at the same time, it still follows the rules and we still find out stuff about concavity and where they're increasing. But for something like this, you probably could have graphed it using your old techniques just as fast as using the calculus. For our last example, this exponential function, that's what it's going to look like in the end. Starting with our x and y intercepts. Well, if we plug in 0 for y, and we split it up here, e to the x itself is never equal to 0. If you think about the graph of e to the x, draw a little sketch of e to the x here. Remember that it is an increasing function that looks like this, and it has an asymptote right there at y equals 0. So it has no value where it's ever equal to 0. But 2x is equal to 0 at 0. And so just finding the x-intercept, we've already found our y-intercept as well, because we know it has to be at 0, 0. But if you plugged in 0 for x to find your y-intercept, e to the 0 is 1, 2 times 0 times 1 would be 0, so you would find it that way as well. Asymptotes in this one are difficult, and this e to the x graph, as you'll see later on, or as you can see already from the points that are listed, in order to get the inflection point at negative 2, negative 0.541, you're going to need your calculator. And because you're going to need your calculator, a lot of this question could be done by graphing it on your graphing calculator to start with and getting a sense for what the graph looks like. Typically, when this question goes on an exam, they would give you a domain to work with. So you'd also have to label endpoints. Because they'd say go from, in this case, I would guess they would look at going from negative 3 to 0 or negative 3 to 1. And then you would label those endpoints as well. Because this partial asymptote here as x goes to negative infinity is hard to imagine. It's hard to visualize. Okay? If we look at a limiting process for this function, as x goes to positive infinity, 2 to the x gets big, e to the x gets big. Big times big, big. So it makes sense that our graph, as we go to the right, gets bigger and bigger and bigger. But where we get a little bit of a problem here is as x goes to negative infinity. Because as x goes to negative infinity, the limiting process, you would say, well, 2 times negative infinity, that's going to be a big negative number. But e to the negative infinity, if you look to your e to the x graph here, that's going to get really close to 0. In math, 0 times infinity causes problems. Because at first you want to say, well, 0 times anything is 0. But you also go, well, infinity's like really big. So infinity times something's going to be really big. And that really big times 0, depending on what it is, sometimes stays really big, depending if the really big is bigger than the 0. This makes sense. And sometimes 0 times infinity will be 0 if the 0 is more 0 than infinity. That's what's happening in this case. The 0 is more 0 than infinity because e to the x, as x gets big, gets faster to 0 than 2x gets to negative infinity. That's the rough overall thing that's happening. The way that you would see this right now is that you would plug this into your graphing calculator and go, hey, it sure looks like it's approaching 0. And so I guess my big times 0 is more likely 0 than big. And then you could draw an asymptote at that point. If you wrote that on an exam as your explanation, I might get fired. So next, if we look at our derivative, and here factoring makes a lot of sense. Once we get our derivative and set it equal to 0, again, e to the x is never equal to 0, so you're going to get x equals negative 1. And if you do your second derivative, same thing, you're going to get x equals negative 2. So we know that negative 1 is going to be a maximum or a minimum. And we know that at negative 2, we're going to get an inflection point. Both of these you're going to have to get from your graphing calculator anyways. So if you have it from your graphing calculator, you're also going to know that it's a local minimum and an inflection point just looking at your calculator. Might have to play around with your window a little bit to get something that's visually looks well on that. Of course, once you set up your diagrams as well, once you put your critical point of negative 1 for your first derivative test, and you check, sure enough, it's negative before and positive after. The easiest way to see that negative before and positive after, if I scroll up a little bit, is if we have our derivative and it's factored right there. You know that e to the x, because we drew a little graph of e to the x, that's always positive. So really, the only thing that's going to affect whether our derivative is positive or negative is this part of our factor right here, the x plus 1. You can sit wherever you like. And so if we plug in something less than negative 1, so if we put in something less than negative 1, obviously that x plus 1 is going to be negative, so our function is going to be less than 0. And anything bigger than bigger than negative 1 is going to be positive. So we'll have decreasing before, increasing after. And it's usually at this point that I'm going to say, okay, then I know that negative 1 is my minimum value. Because I really like this diagram. The arrow showing down and then up really makes it easy for me to see that that's a minimum. I mean, you could use the second derivative test to look at it, but most people like that for the first derivative test. And then with our second derivative, where it's concave up and concave down, now we plug in negative 2 because that's where our second derivative is equal to 0. Again, here's our second derivative. This is the only thing you have to worry about because we know that 2e to the x is always positive. So again, it's obvious where this one's going to be negative when it's less than negative 2 and positive when it's greater than negative 2. So at this point, if you go to graph it and you have all this information, we know we have our minimum at negative 1 and we've used our graphing calculator to find the y-coordinate. We know we have an inflection point at negative 2, negative 0.541, and we found our x and our y-intercepts to be at 0, 0. Using our limiting process, we found out that there was that partial asymptote at y equals 0. Most likely you would get that from your graphing calculator and see that. And you would also see that it's increasing after 0, 0 from your graphing calculator as well. So those two things combined make this question not that bad. But it is one of those things when you get onto your final exam and you're on the calculator section and there's a graphing thing, use your graphing calculator because it's really powerful and it can find those points a lot quicker. And one of the things that the curriculum is wants to teach you is saying we really want you to know all the calculus behind it, because that's important that you understand how you could find these things without your calculator, and the understanding of how it works is really important. That being said, there are some situations that we're going to work with in real life that, yes, if I really wanted to get downtown, I could run. But if I get into my vehicle and drive there, it's going to be a lot quicker and more efficient. And then I can do what I need to do better and faster and more efficient. I need to get downtown and do some work. So using the car to get me there gets me to where I want to be working, rather than using another method that takes longer. Sure, it's probably healthier for me to run because I'll be in better shape. But at the end of the day, I want to get a certain thing done. And if that's my main goal, then I should use a technique that gets me there faster. So we have to make those decisions in life. And that's one of the things the curriculum is trying to that's why the graphing calculator is there, and they're showing you there's technology out there. If you can harness it, it maybe can get you where you want to faster, and that's important.